Hello and welcome to Golden Geography. Today we're going to be thinking a little bit about Hazardous Earth, a debating unit from the OCR Geography A-level specification. Here it is. We're going to be starting with key question 1, which is what is the evidence for continental drift and plate tectonics? It is divided into 2 questions and we'll look at both of those and some of the key points within them. So we're going to start with question 1A. There is a variety of evidence for the theories of continental drift and plate tectonics. Well, before we have a look at that, we just need to think a little bit about the structure of the Earth. And I hope that this is something that you are quite familiar with. The Earth is spherical and it has made up of layers, as we can see here in the image on the right. We don't know for sure because no one's ever been there, but we think that right at the heart of the Earth is the inner core. Around it we have the outer core, followed by the mantle, and then the asthenosphere upon which the crust, the lithosphere, sits. When we are looking at the structure of the Earth, we can look at it based on the chemical composition it has, or on some of the more physical or mechanical properties that it has as well. So if we think a little bit about those, we can break it down, and this diagram shows us some of the differences that we have here. So we can see right at the very center we have the inner core. It is presumed to be a solid, and many people think that it has elements of radioactive material in it, and that is what's helping to generate the heat here. There are suggestions that it contains nickel, iron, and that temperatures can reach up to 50,000 degrees centigrade. Outside of that we have the outer core, which is a liquid. The outer core is heated by the radioactive decay of the inner core, and the heat dissipates from that then through the mantle towards the crust. The boundary between each of these sections has names. Probably the best one is known as the Gutenberg discontinuity, which is between the outer core and the mantle. All of them have different names. If we look at the mantle, it is 2,900 kilometers thick. It has hot, dense material in it, predominantly iron and magnesium rich solid rocks. And the upper part of it is where we kind of start to find the lithosphere. And we'll talk about that a little bit more in a second. The mantle is key when it comes to the movements of plates and the movement of heat and convection currents within that region. The very outer or upper layers of the Earth, the lithosphere, is made up of the crust, which is solid, and then also the uppermost part of the mantle, the asthenosphere, which is often kind of referred to as like a plastic asthenosphere. So it's not really solid, it's not really liquid. So here we have the kind of key sections of the Earth's structure. Well, how plates move then are dependent on this structure, and we mentioned in there that the inner core is thought to have a radioactive decay element, and that's where the heat comes from, and that heat then is moving through the different layers, predominantly through the mantle, and as it does that, that is one of the mechanisms by which plates move. There's actually 3 different theories that we can look at here. Some scientists think they work independently, some think they work together. The most traditional of which is convection currents, and that's the idea that hot magma moves up through the mantle towards the asthenosphere, and that heat causes it to rise. When it reaches the asthenosphere, it's cooling, that heat is being lost, and then that magma cools, condenses, and cycles back round. Hotspot theory is the idea that there are particular parts of the mantle that are particularly hot, and that hot, very hot magma is rising to the surface, focusing on a particular area and driving it, moving it apart, moving the plates in opposite directions. Ridge push and slab pull theory kind of builds on that, and it's the idea that where the hot spot is rising and focusing on that particular part of the crust, it is splitting and fracturing, and new crust is being formed, new oceanic crust, and that's pushing. At that point, the plates are being pushed apart, and as they're pushed apart, they cool and condense, and eventually, millions of years later, they are much denser, and then that density helps draw them back into subduction zones and back into the mantle. That's kind of pulling them back. So probably the best way to look at this is to think about those three together and how they function to cause our plates to move. Well, if our plates move, there must be evidence of it. And this man, Alfred Wegener, was one of the men that was right at the forefront of this and thinking about the movement of plates. He had observed several different key things that were used as evidence to support this idea of plates moving, even though at the time he didn't know the mechanism behind it. Evidence has been found, such as paleomagnetism, the age of seafloor rocks, evidence from ancient glaciations, and fossil records. And we'll look at those one at a time. So first of all, we have paleomagnetism, where you have upwelling of magma and fracturing and rift valleys being formed and new oceanic plate being created in a mid-oceanic ridge area. That new magma, as it cools and creates oceanic plate, the chemical composition of it, any ion within it, will align itself with north-south. So when you're looking at the oceanic plate, particularly places like the Atlantic, we can see where there have been changes in magnetism, switches between north-south pole, and that's been recorded in the rocks itself. So we can see on opposite sides of the Atlantic where we've got matching patterns. So we can look at it and go, well, okay, if they're identical, at one point they must have been joined together. Therefore, now they're separated, even though they're identical in their paleomagnetism. Therefore, we have evidence. They must have moved apart. They must have been formed at the same time and moved apart since. We can see that again with the age of the rocks. So where they are formed together at the centre in that Rift Valley region, they have the same age. They are created at the same time. And if we date the rocks moving outwards in opposite directions away from the Rift Valley, we find that the dates match. So those older rocks must have been formed at the same time. Therefore, they must have been formed together and moved apart since. We also find that with ancient glaciations. If we look at areas of the world where we have evidence of glaciation, some of those areas have the same glacial landforms or the same geology, which means they must have been created, eroded, abraded at the same point in time, and therefore they must have been in close proximity, even though they've now moved apart. Same with fossil evidence. We can look at fossils that can't fly, can't swim, but are found in different parts of the world. But because they couldn't fly or swim, those fossils must mean that at one point those parts of what are now different continents must have been part of one supercontinent, a Pangaea. And therefore we have evidence that those plates have moved apart. Okay, 1b. There are distinctive features and processes at plate boundaries. So what actually happens at these plate boundaries? What do we actually see? Well, let's start by looking at a pattern. We've got here a map of the world that shows us the plate boundaries. We've got three distinctive types. We've got divergent, convergent, and transform. You may find that you're more used to constructive and destructive plate boundaries, but do make sure you know the divergent and convergent terms as well. Here we have an image looking and showing us a cross-section of the crust where we'd have all three of those. So transform is where plates move past each other, divergent move where they move apart, and convergent where they come together. So we'll start by thinking a little bit about divergent or constructive plate boundaries. Here, that upwelling of magma, whether it's convection currents or hotspots or both, is forcing the crust to fracture and rift valleys to be formed, and in the gap between them, new oceanic plate is created. That kind of fracturing of the overlying plate will eventually cause that plate to subside a little bit and rift valleys to be formed. Best example is the East African Rift Valley. But even once this process has happened for millions of years, you'll still find rift valleys in the centre of oceans where this process is taking place. We will also find volcanoes and fault lines as key indicators or features at this location. Convergent plate boundaries or destructive plate boundaries, there are different types, and the subduction involved is very much to do with the density and the difference in density. So the most traditional is the convergent of oceanic and continental, where the oceanic crust is denser, anything from 3 grams per cubic centimetre or more, and it will subduct beneath the continental crust, which is 2.7 grams per cubic centimetre. Therefore, the difference in density, the denser one will subduct. As part of that subduction, there is friction generated in something called the Benioff zone, and at that point, the subducting plate can also melt and generate magma that can rise back up through that overlying continental crust. And that creates features that we can see. The key features being a volcanic arc on land. So we'll see volcanoes. You will see ocean trenches as well, where that subduction zone is. Where we have oceanic plates converging, the older of the two will be denser because it's older, it's colder, it's had longer to cool, and therefore its density is greater. So you might only have a difference in density that's very subtle, but it's the older one that will subduct. And we will see some of the key features that we would find at a continental oceanic convergent plate boundary. You will see an ocean trench, but here it will be a deeper one. The deepest parts of our ocean, like the Mariana Trench, are subduction zones where we have oceanic plates coming together. You will also get volcanoes, but this time it will be island arcs that are evidence and key features of this type of plate boundary. And then finally, we will have continental-continental collision boundaries, or convergent plate boundaries. Now, these two continents will have been separated by an ocean. So originally, you would have had oceanic plates subducting beneath one of the continentals. But as those two plates get closer and the ocean evaporates, you will find that actually you end up with just two continental crusts coming in together. And you end up with a bit of a crumple zone, which creates the fold mountains, but also will help create a root as well. So it is a little bit like an iceberg. There's bits you can see, the mountain ranges, the fold mountains, any fracturings that you get within that. But you also get a bit of a root that you don't necessarily see. Here you will find lots of different evidence. You will get fold mountains. You will find plateaus sometimes behind those fold mountains. You'll get fossil evidence within the mountain range themselves. Those are fossils that were once in the sea that have become part of the originally sedimentary rock that has been metamorphosized and folded. You'll get normal faults. You'll find S faults. And you may also find igneous plumes as well, where that root might have melted and elements of igneous rock risen up through the mountain ranges. And then finally we have our transform faults. These are faults or areas where plates just move past each other. They can be in opposite directions, or they can be in the same direction but just moving at different speeds. You don't tend to find as many distinctive features, but you might find elements of the landscape that are misaligned. So in terms of the built environment, it might be roads or fences that are misaligned, or it might be kind of odd features in parts of a river where the river's course has had to redivert after the movement of the plates. Okay, so pause the video, have a little look at these kind of key points, tick them off in green if you're happy with them, amber if you're not quite sure, red if you need to go back and have another look. Thanks for listening.